Okay, welcome to CULINOLOGY 101. Okay, for this week, week 13, you're going to learn about the oil and fats. Yeah, so this one will serve as an introduction to oil and fats. Okay, looking at today's learning objectives, you will be able to understand the mechanisms that lead to autooxidations and photooxidation of unsaturated fats. Okay, so you have learned before what is saturated and unsaturated. Okay, so the unsaturated one is very sensitive to oxidation. Yeah, understand the reaction occur during heating oil. Okay, understand the mechanism of interacidifications of oil and the product's properties. Understand the application of oil fractionations. Understand the physical property of oil and fats. Understand the novel oil and fat replacer. So for the learning content, I'm going to separate into 4 sections. Okay, the first section is oxidation of oil and fats. So we're going to talk about the autooxidation and photooxidations. Then we talk about some of the ways you can use it to separate the unsaturated and saturated, or you can modify the unsaturated into saturated. Yeah. Then we talk about crystallization of liquid fats. Okay. Crystallization is a way to transform a liquid oil to a solid oil. And then how some of the novel oil and fat replacers that is used to address some of the issues or the demands from the consumer. Yeah. Okay, oxidations of oil and fats. There are 2 types: autooxidation and photooxidations. They are very similar, but they have some distinctions. Yeah. Okay, let's look at what is autooxidations here. Autooxidations is basically unsaturated bonds in fats and oil represent active center that may react with oxygens, which lead to the deterioration in flavor of fats and oil. Okay, basically it can lead to a problem called rancid. Okay, rancidity. Yeah, and the rancidity is where the consumer will detect the rancid smell from the oil and fats, and they will reject the oil and fats. Yeah. The undesirable odors and the flavor become progressively more and more intense and becomes very unpleasant as oxidation progresses. Okay, so the longer the oxidations allowed to proceed, the stronger the rancidity will become. Okay, and this is a problems mainly due to the oxidation of unsaturated fats. Yeah. Okay. Unsaturated, as you learn from organic chemistry, it can be monounsaturated or polyunsaturated. Yeah. Okay. Monounsaturated is where the fatty acid only have 1 double bond. Polyunsaturated is where the fatty acid has more than 1 double bond. Yeah, 3 double bonds. Yeah. 2 or 3 double bonds. Yeah, it can be more than that. Okay. Just to illustrate again, the difference between oil and fats. Okay. Basically, oil and fats, right, they are what we call triglycerides. So they have a glycerol, okay, a glycerol with 3 OH group, esterified, okay, so glycerol, okay, molecule, esterified, okay, here they will form the ester bond to 3 fatty acid, and this fatty acid can be either saturated. Okay, if it's got 1 double bond, a few double bond, it become polyunsaturated fatty acid. Yeah. Okay, so there are 3 of them to form what we call triglyceride or oil and fats. The difference when we use oil, when we use fat, oil is when they are still liquid, fats is usually talked about when they are in solid form. Yeah. And usually what happens is that at room temperature, okay, at room temperature, those that are room temperature is usually 24-25 degrees Celsius. Okay, and at this temperature, usually those that is higher amount of unsaturated fats, they are in solid form. Yeah, those that are more towards the monounsaturated fatty acid or polyunsaturated fatty acid, they are usually in the liquid oil forms. Yeah, so you can see from there, if you go to the supermarket, if you look at some of the shelf, look at some of the oil, the coconut oil especially, they are in solid form because inside the supermarket is very cold. Okay, like Coles or Jar Grocer, they are very cold, and usually the coconut oil, right, at that temperature, they are in their solid form. Yeah, because they have higher amount of the 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 unsaturated, the saturated fatty acids here. Okay, let's look at this here. Auto-oxidations. The oxidation reaction can be divided into 3 steps. Okay, of course, it will need to be initiated. Okay, once initiated, it will propagate, and then usually termination is at the end of the reactions here. Okay, and termination usually is too late to terminate. Actually, once it's initiated and propagate, your product more or less will become rancid. Yeah. Okay, looking at the initiation steps. Okay, basically the hydrogen is abstracted from an olefinic compounds, or what we call unsaturated hydrocarbons, to yield a free radicals. So this can be a very long hydrocarbons. Okay, this one is basically this here. Okay, just that they draw it in a different way, because RH, the R can be a long chain hydrocarbons here. Okay, and R dot here is talking about the one of the carbon has formed what we call free radical. Free radical is something that is very unstable, and it can attack another molecules here. Okay, so you can see over here, basically this one is a long chain fatty acid. You can see from here, this one is only represented here. You can have CCCC. Okay, and this is somewhere near to the double bond. Okay, so there's a double bond, which is the unsaturated the bond. Okay, so over here there is a double bond, and what happened, right, is that the removal of the hydrogen will take place one carbon away from the double bonds here. Okay, so they will start to initiate. Okay, this will be initiated. It can be initiated due to a lot of condition. Can be due to heat. Can be due to a certain the composition that actually causes it. Yeah, okay. All right. So what happened, right, is that this carbon, the hydrogen, usually is CH2. Yeah. What happened is that the H has been removed. Okay, due caused by the light or the presence of metals. Okay, once one hydrogen has been removed, this become very unstable. Yeah, this become very unstable, and this is what we call free radicals. Okay, so this fatty acid contains one free radical here. So what happened with the free radical is that it's going to combine with oxygen, form what we call peroxy free radicals. Okay, so now this will react with the oxygen, okay, to form what we call peroxy free radicals. And these peroxy free radicals, what happened, right, is that it's going to attack another unsaturated fatty acid. So basically they will attack another double bond. Alright, so once they attack, they form what we call peroxide, leaving free radicals that is going to combine with the oxygen, and the cycle repeat itself again. Okay, so what happened is that when these reactions occur again and again, more and more of the unsaturated fatty acid will form what we call peroxides. Okay, so these peroxides, peroxide form, right, is usually no importance to flavor deterioration. In other words, when you form this peroxide, there's no smell, there's no taste. Okay, no smell, no taste. It can be good, it can be bad. Okay, the good thing is that there's no flavor deterioration, which is good. But the bad thing is that when that happens, when the peroxide form, okay, to your product, you wouldn't know that your product is actually in the stage of propagation stage of the oxidation, which means that you cannot detect that your product is becoming rancid. Okay, so the bad thing is that you don't know that your product is going to rancid, because what happened with this, the primary oxidation product, the peroxide, is that if you quickly deteriorate or decompose into the secondary and tertiary products here. Okay, secondary oxidation product and tertiary oxidation products. Secondary, they will form what we call those products that includes carbonyl. Okay, carbonyl is like aldehyde and ketones, all these aldehyde and ketones, usually they are flavors. Okay, they will carry certain amount of the they will carry some flavors top of the profile, yeah, as you learn from the organic chemistry. Okay, and what happened with these secondary carbonyl products? They're going to oxidize further. As you learn from organic chemistry, they will oxidize further to become what? Okay, especially the aldehydes, they're going to oxidize further to become carboxylic acid. So you will see over here, they form the carbonyl product here, peroxide, not much taste or smell. Okay, no smell, no taste. But once they decompose to the aldehyde and ketones, they're going to form flavors. Okay, they're going to have certain type of the rancid flavor. And when they decompose further to the carboxylic acid, okay, more flavors will form, yeah, okay, and all these flavors, usually oxidation flavors, are undesirable, which means that the consumer doesn't like. And another word is that all these oxidized products usually is what causes the rancidity to the oxidized polyunsaturated or monounsaturated fats, yeah. Okay. In order to terminate, usually is that the free radicals will react with each other to form a non-reactive, but usually, as I mentioned, the termination state is too late, yeah. Alright, because your product is already in the process of forming the secondary and tertiary products, and your products will become rancid. Okay, so usually this is the cycle initiation step. Okay, the peroxide value will increase significantly, and they will start to form the secondary and tertiary the flavor components here. So it's very important. That's why it's very important that you need to stop even the from starting. Okay, even from initiating, you need to stop. Alright, it shouldn't be happening. That's why determining the amount of peroxide value to your oil is very important, because if that you have detected certain amount of peroxide in there, okay, through using the chemical titration or some other test, okay, then you need to reject your oil from even using it to produce your product here. Okay, because once initiated, it cannot be stopped. So these are some of the factors that can affect the rate of auto-oxidations, the amount of oxygen presence. Okay, so it's very important for you to remove oxygens, especially to your raw oil. Degree of unsaturated of the lipids. Okay, if you compare between the monounsaturated and polyunsaturated, monounsaturated will be more stable compared to polyunsaturated. Yeah, mono only got one double bond, poly can have two or three or four. Yeah. Presence of antioxidants, very important. If you got antioxidants, you can protect your oil from going rancid, yeah, or going for auto-oxidations. And if you present all these pro-oxidants, okay, all these pro-oxidants can be from your ingredient itself, yeah. Like for example, the presence of copper, okay, heme containing compounds, okay, heme containing compound is very profound in meat products, okay, or meat itself. Liposidase, okay, for meat, okay. Natural nature of packaging materials, whether it will expose to light or not, okay, okay, light exposures. But the thing is that a lot of packaging nowadays, right, they allow the consumer to look at what is inside here. Even though there is much more better and consumer can see what they are buying, but when they expose to lights, it can be actually deteriorate your products here. And the last one is basically the temperature of storage. Alright, the storage usually, the lower temperature will usually reduce the oxidations here. Okay, so the next one, right, is photooxidation. Photooxidation is very, very similar to auto-oxidations, whereas photooxidations or light-induced oxidation resulted from the reactivity of an excited state of oxygen, okay, or what we call single oxygens here. The conversion of single oxygens, right, is due to the presence of an activated sensitizer, okay. So if your food product contains all these sensitizer, right, then it's possible that you convert some of the oxygen to the single oxygen, which can attack your unsaturated fatty acid to form peroxides. Okay, and nowadays a lot of products, right, and also due to the demand of the consumers, you use all those natural products, natural coloring, like for example chlorophyll. Chlorophyll is basically the green color from, for example, from leaves. Okay, like spinach noodle. Spinach noodle, they say they don't want the coloring, they just want to use the natural color of leaves of spinach. Okay, green color noodle. But the presence of all this green color is due to the presence of chlorophyll. Okay, the chlorophyll from your leaves. And this chlorophyll, right, can become the sensitizer. And if you use all this chlorophyll, okay, to make your noodle, and you use unsaturated fats to combine with your noodle, what happens is that your noodle is going to, the oil that in your noodle is going to go rancid. Okay, so it's very, very important. Sometimes you cannot have everything together. Okay, so if you use like your noodle, you produce using like chlorophyll to produce like spinach noodles, okay, using the chlorophyll and so forth. But then you need to like stop or don't use unsaturated fats. Okay, use saturated fat instead. Okay, because the chlorophyll may actually act as a sensitizer to form single oxygen. Single oxygen will attack the unsaturated fatty acid to form peroxide, and the chain of oxidation will go on and on and on. Yeah, so it's very important that you know. Yeah, myoglobins, like meat products. Okay, the red colors. Okay, myoglobin from the blood. Okay, from the muscle. Okay, they can give you the red colors. Sometimes it contains heavy metals as well, and so forth. Yeah. Okay, so again, it doesn't have an induction periods. Okay, again, they will attack the double bond. The difference between photooxidation and auto-oxidation is that this single oxygen will direct attack the double bonds. Yeah, all right. And the only ways to actually quench, okay, is through using the antioxidants. Yeah, like carotenoid and so forth. All these are natural antioxidants. Okay, like vitamin E and so forth. Yeah. Okay, the next one, let's talk about heated oil and fats. Okay, heated oil and fats is a very important sort of like reactions during deep frying of your products. Yeah, deep frying usually is what we call juicy. Yeah, when you form product is juicy. So when talking about deep frying, is where the food is heated by immersing into hot oil. Yeah, commonly practiced in commercial frying and the food service operations. The temperature can be very, very high, from 160 degrees Celsius to 195 degrees Celsius. At the lower frying temperature, frying takes longer time. Yeah, okay. So if you deep fry at lower temperature, it takes longer time, and also not only longer time, the oil will be absorbed more, okay, into your products. Okay, that's why if you fry at low temperature, right, and the oil absorb, right, it becomes very, very oily, and some people say that it's not desirable. Yeah, okay. Higher oil, they actually form the crust, they stop the oil from uptaking into your food. Yeah, that's why sometimes it's better to deep fry at high temperature, then only you transfer to lower temperature. Yeah, double fry, and then you see that the fries is very, very crunchy. Yeah, okay, and there's not a lot of oil soaked inside. Yeah. Deep frying is a complex process involving both the oil and the food to be fried. If you're looking at this diagram, okay, from here is basically the food throwing into the frying oil. So this here is the frying oil. Okay, the food go inside. When you dunk your food into the frying oil, what happens is that the throwing into it will lead to aeration. The aeration will induce oxygens, and because of the high temperature of deep frying, 160, 180, the oxidation will be faster. Yeah, and produce a lot of all these products. If you look at this secondary and tertiary product, which is not desirable flavors. Yeah, okay, because it's what we call the rancid flavor. That's why a lot of times, right, the deep frying oil usually are highly saturated. Okay, highly saturated to prevent the oxidation from happening. Yeah, okay. Later you will see that they actually, the next slide, you will see that they actually have some determination of how long it can deep fry. Usually is the saturated fats that are used to deep fry, because it can last longer and they can prevent all this rancid or flavor compound from happening. Yeah. Then of course the oil will absorb inside. If you have a lot of all these secondary and tertiary flavors, you're going to absorb into your food as well. Okay, that's why sometimes, right, when you deep fry too long, too many times, your products, right, can have some undesirable or rancid taste here. Okay, not only that, the food will start to have certain components from the food start to solubilize in your oil. Okay, and it can be color compound, it can be flavor, and so forth. Yeah, sometimes this can be desirable. Yeah, because whatever you have cooked before, if you deep fry again, the flavor can actually go into your products. Yeah, that's why there is one of these restaurant that actually the fats and the lards, okay, the lard that have been used for century, for 100 years. Yeah, okay, if you can see this century lard, okay, in the Google, you can find that. Yeah, basically they have been using the same lard, they just add on it. Yeah, and to deep fry, to make their burgers. Yeah, okay, because whatever has been solubilized, the flavors they be absorbed into, they make it more and more stronger smells. It's possible as well. Okay, but as long as you don't form too much of all these secondary and tertiary products, which is the rancid smell. Yeah, and because the food also contains moisture, okay, it will vaporize. Okay, of course the water will evaporate, and the water will lead to hydrolysis of your fats as well, which is basically the deep frying oil. Okay, lead to hydrolysis. Again, okay, the hydrolysis can be good, can be bad. Okay, because it can cause the formation of free fatty acid. Free fatty acid actually is something not good. Yeah, because free fatty sometimes can be pungent. Okay, can be smelly as well. Okay, so for deep frying oil, right, usually they have what we call the active oxygen test to test how long it can last. Yeah, AOM, yeah, active oxygen methods. Yeah, the longer the AOM time, the more stable it is. Yeah. Okay, deep frying or shortening, usually it should have 200-300 hours. Yeah, so it can deep fry very, very long. So all the fast food restaurants, they usually use those that have a longer shelf, longer lifetime of the deep frying oil. Yeah, 200-300 hours. Yeah. Okay, so you can see from here the AOM values. They usually, what happens is that they accelerate through bubbling the air through the oils. Okay, and heated at 95 degrees Celsius. Yeah, okay, and determine the peroxide value, how much it has been formed. Yeah, those there is a lower amount of unsaturated fats, okay, or fatty acids, and polyunsaturated fatty acids, they actually are more stable. Yeah, in against formation of peroxide. Yeah. Okay, so I have mentioned before the oxidations and the autooxidation, and both the photoactivations, they usually is due to the attack of the unsaturated fatty acids in the triglyceride. Okay, so what happened, right, is that industry usually will have a certain type of the actually they will do what we call the interestifications. Okay, to exchange. Interaction is basically the exchange of the fatty acids. Usually is to reduce the amount of unsaturated fatty acid in the every single of the triglyceride. Okay, so they're going to reduce that and make it more stable. Yeah, sometimes because of the mixture. Okay, usually oil and fats, they have a mixture of the polyunsaturated and saturated fatty acids. So what happens, right, is that the triglycerides, they can separate. Okay, they can separate. They take out what we call the amount of those fats with the higher amount of the monounsaturated and polyunsaturated fats, and then retaining the saturated fatty acids. Yeah, those triglycerides with the saturated fatty acids. So making it more stable. Yeah. Okay. Okay, let's look at here. Yeah, let's look at what's interacidification here. Interacidification is a process that changes the position of the fatty acid radicals on the glycerides in the fats through randomization or interchange here. Okay, interacidification is used in order to modify the crystallization behavior, modify physical properties. Okay, produce solid fats for margarine and shortening that are low in trans fatty acid here. Okay, you have learned before what we call the hydrogenation. Hydrogenation is basically to add the hydrogen to the double bonds, making it from the unsaturated to saturated fatty acids. But during the process, right, can lead to the formation of trans fats, yeah, which is not desirable, yeah, as you learn from the organic chemistry. Okay, unlike the hydrogen process, interacidification process do not destroy the polyunsaturated fatty acid because they are changing, okay, switching the fatty acid components here. So what happened, right, is that, okay, no need to look at that. Let's look at this one. Usually, if you want to have an interacidification process, usually is that you take a triglyceride, okay, you react with another type of triglyceride, yeah. So you add a triglyceride with another form of triglyceride, okay. One triglyceride is usually more of the saturated fatty acids. For example, SSS. SSS over here, right, is talking about the glycerol with saturated fatty acid, yeah. Whereas this one, only saturated fatty acid. This is what we call the stearic acid, okay. Stearic acid, okay, with 3 stearic acid in there. This one is basically a triglyceride with 3 of the oleic acid. Okay, stearic acid is a fatty acid about 18 carbon long. Okay, 18 carbon long with no double bond, yeah. Okay, whereas oleic acid is 18 carbon long with 1 double bond. Okay, with 1 double bond. So you can mix, like for example, you take the oil with 50% of this and 50% of this. When you react them together, they're going to change. Okay, they're going to interchange their fatty acid. You form about 12.5%, okay, of the original. This one you can see they have a mixture of the composition already. You see, from S become SOS, OSS, SOO, OSO, and this one is the original over here. So once they form this, what happened? Okay, all this they no longer is the fully saturated. They have 1 double bond already. Okay, whereas this one they no longer have those that is fully unsaturated. They have saturated already. So basically they change the physical properties of the resulting oil already, okay, because of the changes in the fatty acid. Okay, so you can see from here, as you react, the pure triglyceride is going to reduce the components. The one that is mixture is going to increase in the concentration here. Okay, this is basically like the examples of the effect of interacidification. You can see from here, the cocoa butter usually they have a very sharp decrease in the melting point, decrease in the amount of the solid. Okay, so from here it is sharp. When you reach about 34, 35, then the solid content going to drop very significantly. But if you look at the interacidified the cocoa fats, what happens is that it takes longer time to achieve that. Yeah. Okay, so the solid fat content remain high even up to like 40 degrees Celsius. Okay, still got about 20%, even at 40 degrees Celsius. Okay, 30% of solid fat. Yeah. Okay, usually in order for the fats to observe or to look at just to be show as a solid, right, you need at least like 15% of the solid fat. Yeah. Okay, anything below 15% you'll be liquid. Yeah. Okay, so interacidification process can be only be carried out at temperature above the melting temperature, which means that all of them need to be in liquid form. Yeah, interacidification process can also be carried out at temperature below its reference melting. In this case, if you go below, then those liquid fraction only can react. So you can use it as a selective as well. Okay. A number of catalysts can be used, including alkaline metals. These catalysts are extremely susceptible to destruction by water and free fatty acids here, and also affected by peroxides, carbon dioxide, and oxygens here. So you need to actually, if you want the interacidification process to go on, okay, you really need to take care of the catalyst. Okay. The next one is what we call the fractionation lipids here. For fractionations, what happens, right, is that they will cool it down. Okay, so what happened, right, is that, as I mentioned, all the oil and fats, right, inside there's a mixture of the triglyceride with higher amount of saturated fats. Some triglyceride have a higher amount of the unsaturated fatty acids here. So if you want to separate them out, so what happens is that you can go through fractionation as well. Fractionation, no problems with the fatty acid, because it's just using the physical method to change here. So what happens is that the fats, they're going to, before they're being separated, all of them are changed into the liquid forms. Once all of them in the liquid forms, then you start to cool it down. Okay, you cool it down. When you cool to about, maybe just say about 50 degrees Celsius, okay, those that with that can some of them with the the lower melting point. Okay, just to continue with that, what happened, right, is that those with the lower melting point, okay, those with the lower melting point will start to will remain as a liquid. Those higher melting point one will start to become the solid. So what happens is that you can actually press out the solid, okay, and the liquid portion will actually be removed from the solid fractions here. Okay, so this is a way for you to form what we call the fractionation, or lipids with two different type of the melting temperature here. Okay, so those that is solid, okay, will be removed from the liquids. So this is what we call fractionations. Okay, the next one is basically what we call the crystallization of liquid fats. All right. So in order to crystallize, okay, you can actually go through what we call the cooling rate. Yeah. So what happens, right, is that you can actually go through either using a supercooling rate or the high supercooling rate, low supercooling or the high supercooling rate. What is the difference between low supercooling rate and high supercooling rate? Is basically the low supercooling rate is that you cool it down slowly, whereas the high supercooling rate, you cool it at a faster rate. So there's a very big distinction here. What happens is that if you cool it slowly, they're going to form a large crystal, whereas the high supercooling rate, you're going to form a small crystal. And this got impact to both the mouthfeel as well as the observation, because if you do it at the low supercooling, the large crystal can actually feel grainy in your tongue, as well as sometimes you can visualize it to be grainy as well. Okay, so this is very true. For example, those ice cream with a very high fat content. Okay, so if you actually cool it at the lower cooling rate, you can form a very grainy, very rough type of the ice cream. Okay, so you need to go through a very fast cooling rate. Yeah, this is one of the example. Sometimes when you cool the ice cream, okay, when you take it out for too long, it become a bit liquid already, and you put in the freezer, the ice cream that you eat sometimes is not desirable because it has very large crystal. The crystal can be either fats, it can be the water as well. Okay, so if you look under the microscope, okay, the microscope, the high supercooling rate, you can see they're very smooth, no very small crystal, no very small crystals, and a lot of nucleation, but very small crystal. But whereas this low supercooling rate, not much of the nucleations, but all the crystals are very big. You can see, okay, and the big crystal can actually give you the grainy type of the mouthfeel. So the hardness, as I mentioned before, okay, the hardness, the solid fat content can be as low as 12% to 15%, yeah, and the fats will retain as a solid characteristic. Alright, so the fats, and this one is basically what we call the solid fats, yeah. Okay, solid fats, which means that they remain as solid. That's why sometimes, right, in the butter, if you take out from the fridge, okay, it's very hard. But if you put at room temperature, what happens? Some of the triglyceride will start to melt, okay, changing to liquid form, correct or not? So because of that changing to liquid form, the amount of solid content in the butter when you put it on the room temperature is going to start decreasing. When it decreases down to about 60-70%, you see that it's very, very soft, but it's not liquid, it's not pourable. When you press, very, very soft, it's like liquid because it's still holding. As long as it's above 12 to 15%, it still have this solid characteristic. But if you leave it leave it longer a bit and allow the temperature increase a bit, what happens is that the butter will directly break into liquid form. Okay, they no longer can be observed as a solid form. You become a pourable liquid. Okay, and that is below the 12% solid fat contents here, and that can be tested through the penetrations here. In the R&D kitchen, you can see that beside the lab, you got this machine where you can test the hardness of the object, yeah, and in this case, talking about the solid fats. Okay, so you can see from here, if the solid fat is very high, the penetration to the mass is going to be very, very shallow. It's only like about like 30 mm, for example. Okay, whereas if you have this not 30 mm, 0.30 mm. Okay, so if you have very, very low solid fat, what happens? It can go deep inside. Okay, they have a larger penetration, yeah, because of the decrease in the solid fat, yeah. So you can use this to test the hardness of the your fat crystal or anything. Okay. Okay, let's talk about novel fat and fat replacer. As a consumer demand more and more of the low fat food. Okay, but again, a lot of people they demand for low fat food. Okay, but they still need the juiciness from the fats. And sometimes it's also that the industry, they want to use all these what we call the fats. Okay, they don't want to say that this fat has been modified or whatever. Okay, they still want to have a very high stable, okay, high stability type of oil for the industry use, but the name they need to retain. Okay, so what happened, right, is that they actually can create a novel fat, okay, through genetic engineering. They actually change the plant, so the plant no longer produce those fatty acid, okay, the fats with the high polyunsaturated fatty acids. They may produce, okay, the fats with monounsaturated fatty acids or saturated fatty acids, yeah. Okay, with that, they still can retain the name, okay, canola oil. Alright, but without you realizing, the canola oil has a lower amount of the polyunsaturated fat. Instead they have higher amount of the monounsaturated fatty acids as well as the saturated fats here. So they actually can produce those with the low linoleic acid canola oil, low linoleic acid soybean oil or linseed oil. Low linoleic, okay, linoleic is basically a polyunsaturated fatty acid, yeah. Okay, now they become low. Okay, with the low content of this, what does it mean? Now the canola oil produced from the plant is stable against oxidation. Okay, and you can actually market the other way around. They call it as a high oleic sunflower oil. Okay, because they have higher amount of this oleic, which is monounsaturated, not polyunsaturated. Yeah. Okay. Another way, right, is that you can produce some fat replacer. Yeah. In this case, is what we call olestra. Olestra is basically esterification between sucrose and the fatty acid. Yeah. As you know, as you learn from organic chemistry, the sucrose is made of or it composed of a lot of hydroxyl group. Okay, hydroxyl group. Hydroxyl group can react with fatty acid or carboxylic acid to form an ester bond. So instead of the conventional glycerol can only form a ester esterified with 3 fatty acid. Now it can esterified with 8 fatty acid. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now instead of 3, it can form 8 fatty acids. So all this olestra, again, you can see sucrose over here, the OH group has been esterified with fatty acids. Okay. Although it still has some oily characteristic because of the presence of fatty acid, but this is way too big to be absorbed or hydrolyzed by the stomach enzyme. Okay, and cannot be digested by the stomach enzymes. Okay, and not in stomach, the colon enzymes, and so it cannot be absorbed into our body and contributed to the calories here. So this one will most likely end up coming out from the feces here. Okay, so I'm going to end here. If you got question, please ask in the palette. If you got no question, please indicate no questions in the palettes. Okay, thank you very much.